every integer is either even or odd, and there is a nice way in which this interacts with addition. If you add two even numbers, the result is even. If you add an even and an odd number, the result is odd. And if you add two odd numbers, the result is even. In this video, we're going to define what it means for a permutation to be even or odd, and we will see that composing permutations behaves just like adding even and odd numbers. Unfortunately, the definition is going to be a bit harder for permutations than it is for numbers. So here is that definition. A permutation is odd if you can write it as an odd number of transpositions, and even if you can write it as a product of an even number of transpositions. So remember, a transposition just means a two cycle, so that, for example, the identity permutation, well, that's equal to 1, 2 times 1, 2, which is a product of two transpositions. So the identity is even. Okay, on the other hand, if you had a single transposition, well, that's a product of one transposition. So 1, 2 is odd. But if you had a three cycle, like this, you have seen that we can write this as 1, 2 times 2, 3. That's a product of two transpositions, an even number of transpositions. So the three cycle, 1, 2, 3, is even. And in fact, in general, you've seen how to express a m cycle as a product of m minus 1 transpositions. So it will follow that every m cycle where m is even will be odd, and every odd length cycle will be even. We'll come back to that on the next slide. We also talk about the sign of a permutation for a completely related concept. So the sign of a permutation S, which we write like this, is 1 if the permutation was even and minus 1 if the permutation was odd. So for example, the sign of the identity would be 1, and the sign of the three cycle 1, 2, 3 would also be 1, but the sign of a transposition, so 2, 7 for example, that's an odd permutation, so its sign is minus 1. Okay, now there is a problem with this definition, a kind of serious problem, especially in the way that we've defined the sign of a permutation, because we know that you can write, for example, the three cycle 1, 2, 3 as 1, 2 times 2, 3. So I said, okay, that means that 1, 2, 3 is even. But couldn't there be some other way of writing the three cycle 1, 2, 3, this time using an odd number of permutations? It doesn't seem at all obvious to me that you couldn't do that. So at the moment, it seems like there's a real problem with our definitions here, which is that maybe there are some permutations which can be written as a product of an odd number of transpositions and also as a product of an even number of transpositions. So those permutations will be both even and odd, and this sign function wouldn't make sense at all. So we're going to leave this problem for now. We'll come back to it in the final video where we'll prove that actually every permutation is either even or odd, but not both. But for now, we're going to take it for granted that this definition really does work, and we will assume that it's impossible to write any permutation both as a product of an odd number of transpositions and as a product of an even number. So under this assumption that it makes sense, I just want to prove a couple of results about the sign of a permutation. So remember that if S can be written as a product of m transpositions, well, if m is even, then we say the sign of S is 1, and if m is odd, then we say the sign of S is minus 1. So you could rephrase that by saying the sign of S was minus 1 to the power m if you can write S as a product of m transpositions, because minus 1 to an even power is 1, and minus 1 to an odd power is minus 1. So what that helps us to do is just to give a really simple proof of this proposition here, which says that for any two permutations S and T, the sign of S times T is the sign of S times the sign of T. So the reason that that's true is because if you write S as a product of, let's say, K transpositions, so T1 up to Tk, so those T1 up to Tk are transpositions here, and if you write T as a product of transpositions, so let's say, I don't know, V1 up to VL, where again V1 and VL are transpositions, then st is equal to, well, I can just take my expression for s and my expression for t. So I can express s times t using k plus l transpositions. So if we want the sine of st, then as we just observed, that's minus 1 to the power of the number of transpositions in an expression for st. So k plus l in this expression here. So that's just minus 1 to the k times minus 1 to the l, which is the sine of s, times the sine of t. Okay, so there's nothing really happening there, but it's just a nice observation that the sine of a product like this is equal to the sine of the first thing and the product times the sine of the second thing. We can even prove some more things about the sine of a permutation very easily. So firstly, that any even length cycle is odd and any odd length cycle is even. And the reason for that is that we saw that, so the proof for part 1 is just that you know that for any cycle like this, so an m cycle can be written as a product of m minus 1 transpositions So we saw this in the last video. So you can write your m cycle using m minus 1 transpositions, and of course if m is odd, then m minus 1 is even, and if m is even, then m minus 1 is odd. So that's all you need to prove the first part. And for the second part, well, if s is any permutation, then the sine of s and the sine of the inverse of s are the same, and the reason for that is that if you write s as a product of transpositions, just as we did above, well then, what's s to the minus 1? So you know how to find the inverse of a product. You know that if you have the inverse of a times b, then that's b inverse times a inverse. So you just take the product of the inverses in the opposite order. So s inverse here would be tk to the minus 1 times tk minus 1 to the minus 1, all the way down to t1 to the minus 1. But these things are transpositions, and if you have the inverse of ab, well, that's just ab again. Right? Transpositions have order 2, so they are their own inverse. So this is just tk times tk minus 1. Let's write that a bit more clearly. All the way down to t1. So we've written the inverse of s using the same number of transpositions as it took to write s, and therefore s and s inverse have the same sign. Okay, well, why are these things useful? Well, one of the reasons that these things are useful is that it actually allows us to compute signs of permutations very easily. Because if somebody gave you, for example, they asked you, what is the sine of, let's say, 1, 2, 3 times 2, 7, 9, 4, well, you can just say that this is the sine of 1, 2, 3. I need an extra set of brackets there, times the sine of 2, 7, 9, 4. Okay, 1, 2, 3 is a 3 cycle, so it's even. So this is 1. And 2, 7, 9, 4, that's a 4 cycle. Even length cycle are odd, so the sine of this is minus 1. So this is minus 1.